This is our ETE 210 final project, temperature sensing controller. This project was completed by Rob Hilgendorf, Angelo Mole, and Adam Sullivan. This is our temperature sensor controller. What we have here is we have a schematic of the design, and we'll get into that in a little bit more detail. We have a 12 volt DC power supply that we're using to provide power. We have the actual circuit that's been constructed on a breadboard, and we have a fan that we're using for cooling. I also have a meter that's hooked into the output of the comparator just so that we can see that state change when we hit the set point. So what we have here is we have an LM35 TO92 package temperature sensor. This temperature sensor operates from 0 to 100 degrees C, and the voltage output on this sensor is 10 millivolts per every degree C. So at 0 degrees C, the output is nothing, and at full range, 100 degrees C, we have a 1 volt output. We're using a comparator, and we have a voltage reference that's set, and we can adjust it with this pot. So that when the voltage output of this temperature sensor exceeds our reference voltage, the comparator output will go low, allowing negative current to flow from the base of our 2N3906 transistor, allowing us to conduct our 12 volts between the emitter and collector, which will energize our relay and turn on our fan. So the temperature sensor, the circuitry, and the relay controlling the fan, that is the basic part of the project. We've also added an additional feature, which is this bar LED graph, just so that you can see as the temperature sensor is heating and cooling, it just kind of gives a nice visual indication of that. So let's go ahead and take a look at the circuit actually operating. Because that temperature sensor operates in degrees C, and I have the set point set to 100 right now, I'm going to have to heat it with a lighter because just touching it is not going to be enough. So the things that we're going to be looking for here, and I'll try to heat it slowly so that we can see, but we will be able to see the bar graph move up, and when we get to the 20th LED here, which will be our 100 degrees C, we'll see the output of the comparator go low. We have a blue LED on here indicating that the relay has been energized, and then we'll be able to hear the fan turn on. The fan will stay on and the output of the comparator will stay low until we drop back below that set point. So I'm going to go ahead and try to heat it slowly, and we'll see what... Okay, so now we've reached a set point. Our comparator output voltage has gone low. Our fan is turning until we dip back below that set point, and then we'll start to drop again in temperature. And we have that visual indication. So I'm going to go ahead and heat it up again. And we're approaching. Now we're on. We got our LED indicator here and our voltage. I'm going to go ahead and heat it up a little bit longer this time, so the fan will stay on a little bit longer. Comparator output low, back high again. And now we can watch our visual indicator as this climbs back down to room temperature. And that's our project. We've seen the circuit work, but what makes up the design? The design consists of 4 sections: the power supply, the temp sensor section, the fan output, and the light bar temp indicator. Zooming in on the temp sensor, at the heart of this circuit, we have an op amp that's being used as a comparator. We have our 12 volt source coming in through a precision voltage reference, a voltage divider, a buffer, and into the non-inverting input. On our comparator, we use pot P4 to adjust that voltage reference depending on the set point we want, and we've done those calculations and included them on the schematic. We have our voltage output coming from the temp sensor that is going to the inverting input. When that voltage exceeds our voltage reference, the output of the comparator goes low, allowing current to flow from the base of our 2N3906 transistor, allowing our 12 volts to flow from emitter to collector and out to our relay. The fan output section is a very simple section. We have our signal coming in from our 2N3906 into the coil, energizing the coil, closing our contact on the relay, supplying 12 volts through that contact to our fan. The light bar indicator uses two display drivers. We use TP3 and TP4 to set our low and high temp set point using a voltage divider with potentiometers and the internal voltage reference of the ICs. We have our signal coming in from our temperature sensor into the signal inputs on the ICs. Once we exceed our low temp set point, we light LED 1. When we exceed our high temp set point, we light LED 20. Our low temp set is at 22 degrees C, just above ambient temperature, and our high temp set is at 100 degrees C. So we're covering a range of about 80 degrees C. We have 20 LEDs, so we're showing a 4 degrees C temp rise on each LED. So every 4 degrees C temp rise we see, we light up another LED. Just in case you're interested in doing this circuit on your own, we've included a parts list of all the parts that are required in order to make this circuit function. We included some of the things that we needed to consider, the transistor current calculations to ensure we didn't exceed the current limitations of the transistor when we're driving the relay, the voltage table for the output of the temperature sensor, the input voltages for the light bar indicator, our set points where they're currently set, and also some reference voltage settings for the reference voltage for the comparator. In our configuration, we use the cooling fan just as you would if you were cooling a component on a motherboard that's exceeding a certain temperature. But there's also other uses for this circuit. You could use it just to simply send a signal to a control board calling for your AC unit to turn on your house, similar to your thermostat. Or you could use a heating element instead hooked into the normally closed relay contact to maintain a preferred temperature, such as they do in the travel coffee mugs or in a hot water heater. There's endless possibilities for this temperature control circuit. And that's a wrap. I hope you've enjoyed the video and maybe even learned something. Thanks from Rob, Angelo, and Adam.